Network theorems look intimidating only until you realize you already use their logic whenever you simplify a complex problem in real life. Welcome to the Learning Studio, where we don't just teach subjects. We break them down to their core intuition so you understand why methods exist, not just how to apply formulas. Most students see network theorems, Thevenin's theorem, Norton's theorem, and the principle of superposition as abstract shortcuts invented for exams, but in reality, they were created to handle complexity in a practical and reliable way. Electrical networks can quickly become too large and too complicated to analyze directly, so engineers needed a systematic method to simplify them without losing accuracy. To see this intuitively, imagine navigating through a crowded city. Instead of memorizing every single street, you focus on the main roads that affect your journey, temporarily ignoring side lanes that don't change your final outcome. Network theorems do the same thing for circuits. Thevenin's theorem replaces an entire complex network with a single voltage source and resistance. Norton's theorem does the same using a current source and resistance, and superposition allows you to study one influence at a time when multiple sources act together. At a deeper level, these theorems rely on the linear behavior of electrical components, where responses add up predictably. This makes it possible to break a complicated circuit into manageable pieces, analyze each part independently, and then combine the results to understand the full system. Instead of solving everything at once, engineers reduce complexity step by step. On a much larger scale, the same logic is used in power systems, communication networks, and electronic design. Engineers simplify subsystems to test stability, predict performance, and identify faults without rebuilding or recalculating the entire network. Whether it's a power grid, an amplifier circuit, or a signal processing system, network theorems allow complex behavior to be understood through simple equivalence. In practical engineering work, these theorems are applied when designing power supplies, analyzing electronic circuits, optimizing load conditions, and troubleshooting real hardware. They were later formally defined and standardized by engineers like Hermann von Helmholtz, Leon Charles Thevenin, and Edward Laurie Norton, ensuring that circuit simplification followed consistent and reliable rules across the world. Now that the intuition behind network theorems is clear, the next step is to apply them numerically through step-by-step circuit examples, where simplification turns into precise calculation, and that's exactly what we'll cover next here at the Learning Studio.